The standard waveguide we take as a circular core cross section, but nowadays the optical waveguides having non-circular cross section may have planar, rectangular, elliptical, polygonal, and other type of cross sections also used. The planar waveguide is generally used in integrated optical devices. For the planar waveguide, any lateral confinement of light is not observed, but in the case of the rib waveguide, lateral confinement is present. Metal-clad optical waveguides are of considerable current interest as they have been shown to possess an extremely large differential attenuation between the TE and TM polarizations, and thus can be designed to act as efficient integrated optic polarizers. A metal cladding is also used for applying electric or magnetic field on an optical waveguide for electro-optic or magneto-optic modulation. In integrated optics, metal-clad waveguides play a very important role because they show distinct properties which are very useful, and the conducting regions facilitate making electrical connection with the other circuits. Rib waveguides and channel waveguides consist of rectangular or nearly rectangular cores. Considerable amount of work has been done based on the analytical and numerical methods to obtain approximate solutions corresponding to rectangular core waveguides. Some other cores wave non-circular cross-sectional waveguides which have been investigated recently are those with square, triangular, pentagonal, and cardioid cross-sectional. A waveguide in which two cores are embedded in the same cladding have also been investigated. Well, in the beginning, people used only dielectric material as a waveguide material, but in due course, many other new materials like polymers, liquid crystals appeared and remained very successful in the fabrication of waveguides. Waveguides having their guiding region filled with chiral materials are known as chiral waveguides. These waveguides may be used as directional coupler, etc. Well, these waveguides already I have explained you in the previous slide. These waveguides with non-circular cross sections. Now we use some approaches which we use to find the number of possible modes sustained through the waveguide. We are using so many methods for this purpose, but the most common method is the analytical method, which we use to determine the modes through the waveguide. So Maxwell equations along with the given set of constitutive equations for material are solved under a given set of boundary conditions to understand the guiding behavior of a waveguide. There are two approaches which are used to find the field pattern in the waveguide. When the dimension of the waveguide structure is large enough in comparison with the wavelength of light, we can use the ray theoretical approach for analysis the optical waveguide. Assuming that the wavelength of light is much smaller than the dimension of waveguide, the general electromagnetic wave equation can be reduced to the iconal equation, which determines the wave propagation in guide. Maxwell wave equation can be solved directly using the constitutive equations. For the analysis of the waveguide, the boundary conditions are imposed on the wave equation. This is in fact a special case of a more general problem known as an eigenvalue problem, also used in quantum mechanics and other fields. The wave equations obtained from the Maxwell equations along with the associative constitutive equation is generally a vector equation and cannot be solved easily for the most of the waveguide structures. Hence, to simplify the problem, the scalar approximation of the vector wave equation is used, but
Even the scalar wave equation can be solved exactly only in some special cases such as the circular waveguide and the planar waveguide, etc. So new approximations are used to solve the scalar wave equation for different type of waveguides. To get the scalar wave equation, the weak guidance approximation is to be made. Weak guidance approximation means the difference between the refractive index of core and cladding is very small. Now the procedure to obtain the scalar wave equation in the appropriate coordinate system for non-circular cross-sectional waveguide, I can explain you. First step, first we find the normal curve to the original curve, which we use as a boundary of the core cross section. The curve which is normal to the original curve is obtained by using the formula m1 m2 is equal to minus 1, where m1 is the slope of the original curve, m2 is the slope of the normal curve. Thus we obtained two set of curves described by the two parameters, one set being normal to other set. Is that clear? To simplify this problem, we choose a suitable coordinate system by choosing the parameters as the new orthogonal coordinates. The scale factors can be determined by using the formula dz square plus r square d theta square plus dr square is equal to h1 square d xi square plus h2 square d eta square plus h3 square d z square, where xi, eta, z are the new coordinate set, r, theta, z are the cylindrical polar coordinates, and here h1, h2, h3 are the scale factors. Using these two steps, the scalar wave equation in the new coordinate system is obtained. Apart from this, even in solving the scalar wave equation, there may be difficulties because of the other factor. In some non-circular cross sections, sometimes it is difficult or even impossible to separate the variables in the scalar wave equation. This is generally due to the nature of the geometry of guiding structure and the refractive index grading of different regions of the waveguide considered. The other problem is to solve the differential wave equation which is obtained after the separation of variables because of the presence of singularities. Thus, for the study of an optical waveguide analytically, we use some approximations to solve the scalar wave equations and obtain the characteristic equation using the boundary conditions. In order to get the number of modes which propagate through the type of optical fiber, the dispersion curve can be plotted. The whole analytical approach is in spite of the difficulties involved, but it gives better insight than the numerical methods in the study of optical waveguides. So generally, this is the frequently used method to determine the number of sustained mode through the optical waveguide. Now there are some numerical methods used in the waveguide analysis. Well, clearly these methods are more complicated. So despite the widespread use of dielectric waveguides in the microwave region as well as the optical region of electromagnetic spectrum, their characteristic properties are very difficult to find. The analytic approach is suitable only for a few simple geometries, but for a complicated geometry, it is difficult to match the electric and magnetic fields at the interface. Hence, to obtain the solution of these complex geometrical waveguides, some numerical methods are used. In these numerical methods, a common feature is the formation of a matrix eigenvalue equation that is solved for the frequency, propagation constant, and the field in the waveguide. One of the first numerical method was reported by the Collins and Delhi for the solution of the dielectric loaded waveguides. They used the finite difference method to discrete the Helmholtz equation for inhomogeneous waveguides. Some other methods which are used to analyze the waveguides are, say, vector circuit method, finite element method, the matrix approach method, and last goals point matching method, etc. Now we discuss briefly these numerical techniques. So let's we start with the. Well, one of the method is the finite element method. Although there are several methods which have the advantages of only requiring the solution of a small matrix eigenvalue problem. Each of the trial functions is limited to a particular geometry and requires the evaluation of lengthy analytic expressions. A method of approximating a function space that does not suffer from these difficulties is the finite element method. This method is commonly used to heat the fluid flow problem and for complicated electromagnetic problems. In this method, the region of the interest is divided into triangular elements and a polynomial approximation is made of the function in each triangle. Ahmad and Delhi used this method for a dielectric loaded waveguide. The other great advantages of this method are the freedom to fit any polygonal shape by choosing the triangular element shapes and sizes, and the extremely close approximations provided by higher order polynomials. There are some drawbacks associated with the vector variational formulation, which are known to include non-physical solutions. Well, Carnot suggested imposing boundary conditions rigorously to eliminate these problems. So, in this way, we can use the finite element method, but we can say this method is more complicated rather than the analytical method.
In this slide, you have some facts about finite element method.
Now, the another important numerical method is finite difference method. Finite difference techniques are generally used to analyze the field in arbitrary shaped optical system. They are simple to program because they involve calculations with square matrix, and they make efficient use of computer memory. Mostly finite difference methods are based on classical 3-point formula, del 2 psi over del x square is equal to 1 upon h square, psi x plus h plus psi x minus h minus 2 psi x plus OH square. The presence of OH square indicate the term of order h square are neglected, or equivalently, that the formula is correct up to the first order in H. It is not always emphasized that this formula implies that the second derivative must be continuous within x minus h, x plus h. This is never the case when a discontinuity line lies in this interval. Thus, this formula cannot be applied faithfully to a system with step index refractive profiles. This is the limitation of this one, which is the unfortunate, as a step index profile are the frequently encountered. It is then usually recommended that discontinuities be placed halfway between constitutive sampling point, or that the exact permittivity on the every grid point x be replaced with its average on the corresponding mesh. When the refractive index is discontinuous and the second derivative is continuous, this classical 3-point formula contains a zero order error. Many researchers have been studying different waveguide problem using this finite technique method, using this finite difference technique. However, the finite difference method cannot provide sufficiently accuracy. This is the drawback of this one, and major drawback is that it cannot be used for the step index fiber. So it has some limitations. Now, goals point matching method. This is the important goal method, and this technique is generally used numerical, which is popularly used numerical method. It is the Goals point matching method. Basically, goals use this method originally for the rectangular cross section. This method is very useful method for the non-circular cross sections and is widely known in optical fiber literature as Goels point matching method. In general, it is not easy to analyze the model behavior of such non-circular waveguides. As such, various numerical methods are used, but they have some limitations. So, another new numerical method based on the mapping of the molecular dynamics of extraction extreme eigenvalues and the corresponding eigenmode have been applied for the scalar and semi-vector mode analysis of arbitrary shape optical waveguides by Noro, who has suggested to analyze the modeling and optimum design of the lossless optical waveguide using this method. The point matching method involves a rather exhaustive and formidable numerical computation. This method is based on the expansion of the electromagnetic field expressions as series in terms of a set of certain functions. In this technique, such as series involve Bessel functions, modified Bessel functions, and their derivatives multiplied by trigonometric functions. The field solutions must be involve the Bessel functions of the first kind in the guiding region. Because the Bessel function of first kind have no singularities at the origin, in the non-guiding region, the field solution involve modified Bessel functions of second kind, which have a decaying characteristics as the argument increases. Therefore, the field in the guiding region is expressed as a series of Bessel functions of the first kind multiplied by the trigonometric function because it shows the field oscillating nature inside the guiding region. In the same way, the field in the non-guiding region is expressed as the sum of a series of the modified Bessel functions multiplied by trigonometric function because it shows that the field decaying nature as one goes away from the core cladding boundary. The scalar fields and their derivatives inside the guiding and non-guiding regions are matched at some elected points on the boundary. The points are so chosen that they may faithfully represent the geometry of the waveguide under consideration. To obtain the non-trivial solutions, a certain determinant must vanish and form this determinantal equation known as the characteristic equation. One may obtain the model characteristics of the waveguide. Here, I have shown the formula of Goels point matching method. Say, let us consider a waveguide whose guiding region is bounded by an equiangular spiral. For the sake of convenience, we use the scalar wave approximation for the propagation of electromagnetic waves. The equation of the curve in polar coordinate is r is equal to a to the power m theta. In this figure, I have shows the transverse cross section of the waveguide under consideration. For the study of the proposed waveguide, we use Goels point matching method, as I have described you. In this method, we have to solve the scalar wave equation in cylindrical polar coordinates and then use the boundary condition at the chosen point on the core cladding interface. Very well known the scalar wave equation is delta square psi. You know it. Delta square psi minus n square upon c square del 2 psi upon del t square is equal to 0. And you know delta square is the scalar Laplacian operator in the cylindrical polar coordinate system r theta z, where n is the refractive index of the core material and psi is any orthogonal Cartesian component of the electric or magnetic field for the core region. Now, for our proposed waveguide, the solution of the scalar wave equation can be expressed as a series expansion of the solution of the fields in the circular fiber. Using using a harmonic time dependence and also a harmonic z dependence of psi, we can say psi is equal to wave function is harmonic dependent of time and z. Psi is equal to psi naught e to the power I beta z minus omega t. We determine the wave equation for the core region in term of cylindrical polar coordinates, in term of u, where u is the use the omega square mu naught epsilon minus beta square, as I have explained you earlier in the slide. Omega is the angular frequency, and epsilon the permittivity, mu is the permeability, and beta and z component of the propagation vector. Here beta is the z component of propagation vector. While using the separation of variable techniques, we determine the equation for the coregion. This equation represent generally we get from this is the well-known Bessel differential equation, and it represents the order of Bessel function. The solution of this equation are simply the Bessel function. For the core reason, I will not explain basically the equation, because this I have explained in the previous slides. This equation known as the well-known Bessel differential equations, and integers nu represent the order of Bessel function. The solution of these equations are the Bessel functions. In the core region of the proposed waveguide, we can take the solution as a sum of series, where each term is the product of Bessel function of first kind g nu x and the trigonometric function of the same order. Similarly, in the cladding, we have another equation which we get the modified Bessel differential equation. In the cladding region, we take the solution as a linear combination of terms which are product of modified Bessel functions of second kind, that is kvx, and the corresponding trigonometric function. We choose kvx as the acceptable solution in the cladding region because in this region the solution must have the decaying character as one go away from the axis of waveguides. Therefore, if psi 1, psi 2 to be the solutions in the core region and in the cladding region, then we can say, well, psi 1, it is, I have shown, you can see it in the picture. Psi 1 is equal to A0 J0 UR plus A1 J1 UR cos theta plus B1 J1 UR sin theta plus A2 J2 UR cos theta. And psi 2 you get C0 K0 WR plus C1 K1 WR cos theta, basically psi 1 and psi 2 in term of the Bessel function and in term of modified Bessel function. Now we know that for using the Goel's point matching method, the origin must be situated inside the core region. Hence, for using this method, in our case, the origin ought to be shifted to the new position and the coordinate become rho phi instead of r theta. For one complete turn, the spiral starting from A reaches B. In the previous slide, I have shown this point. The points A and B may be joined by a straight line to make the guiding region distinct, where I have shown the picture of this type of waveguide, spiral waveguide. So we can say A and B may be the joined by the straight line to make the guiding region distinct from the cladding. We may also decide not to join A and B, but in this case the core cladding boundary in this region will not be well defined. The coordinate rho phi on AB can be easily determined by the numerical techniques. So in this way we shift the origin to the new origin. Then we choose some number of matching points, say for example 28 matching points, of which 22 are on the spiral and 6 are on the straight line, with their coordinates as rho k, psi k, which k is equal to 1, 2, 3. This point describes the general shape of the cross-section boundary by the spiral. For greater accuracy, we should take very large number of points on the boundary of the waveguide. But for the sake of convenience in the calculation, we take here, say for example 28 point, 25 point, we can say. But if we take the more points, naturally we get the more accuracy. So however it gives the reasonable, we get the new we get the equation in new coordinate system. Then what is the next step? The polar coordinates of the point distributed of the boundaries are serially designated as row 1, phi 1, row 2, phi 2 to row and phi n, say row 28, phi 28, etc. These are in term of the new coordinates system. Now, in case of dielectric core dielectric cladding waveguide of the field solutions and their first derivatives must match continuously at the arbitrary chosen points according to the goals point matching method. So, after matching the fields and their derivative at the chosen point, we obtain the a matrix of a very high number of equations. So after that, for example, in this case, we get the 56 equations. So this is for the field in equations in these 56 equation. So we can accumulate 56 unknown constant A and B and Cs, Ds also ensure the reasonably accuracy. To obtain the non-trivial solution of the set of 56 equations, the determinant formed by the coefficient of 56 unknown parameters must be set equal to 0. So the condition for existence of non-trivial solution yield delta 1 is equal to 0. So this is a general model characteristic equation for the fiber which are proposed cross section. In this equation, the quantities rho k and are related to the phi k by the equation r is equal to a to the power m theta. R and theta can be transferred into the new coordinate system rho phi by the transformation equation for a 6 value of m. It is also be the remembered that if we take more points on the boundary, the characteristic equation will be more complicated. We can obtain the cutoff equation again by setting the w is equal to 0. So in this way, we can determine the possible number of modes sustained through this non-circular waveguides, which are more complicated. We cannot solve easily these structures, these geometries using the analytical method. So goal point matching method is very useful in that case. Transmission of light via an optical fiber has a wide variety of applications. Now we discuss here some applications, some major application which we use by the optical fiber. Say first, the major application is illumination and image transmission. How? Bundle of free fibers whose ends are bound together, ground and polished, form flexible light guides. If no attempt is made to align the fiber in an ordinary array, they form an incoherent bundle in the sense that there is no correlation in the position of the fiber terminations at one end of the bundle with what at the other end of the bundle. The primary function of such bundles is simply to conduct light from one region to another. Such flexible light carriers are relatively easy to make and inexpensive. They are used for illumination purposes. When the fibers are carefully arranged so that their terminations occupy the same relative positions in both of the bound ends of the bundle is said to be coherent. Such a bundle is capable of transmitting images. When one end of such a flexible image carrier is placed face down the flat on an illuminated surface, a point-by-point image of the surface appears at the other end. Endoscopes are such coherent bundles. By allowing direct viewing of what was formerly hidden, it has become a vital diagnostic tool for industry and medicine. Another important use, optical communication. Traditionally, electronic communication were carried out by sending electrical signals through the copper cables, coaxial cables or waveguides. Well, in recent years, optical fibers are being used where light signals replaced electrical signals. A basic communication system consists of a transmitter, a receiver, and an information pathway. Normally, the information to be communicated is a non-electrical message, which is to be converted first into the electrical form. The conversion is done by the transducers. For example, a microphone converts sound wave into the current. Similarly, a video camera converts images into currents. These electrical images are of low frequency and cannot be transmitted directly. Therefore, they are superposed on a carrier wave of very high frequency. The process of imposing a message signal on a carrier wave is called the modulation. Two different techniques of modulations are available. In analog modulation, a continuous wave carrier is in the message. In digital modulation, message is transmitted in discrete form using binary digit. The message travels along the transmission channel and it receives at the receiver. The receiver demodulate of the modulated waves and separate out the message and feed to the transducer such as a loudspeaker. The bandwidth requirement of the message and the bandwidth of the carriers determine the number of messages that can be simultaneously transmitted on an information channel. For example, a bandwidth of 4 kHz is required for voice transmission, while 6 MHz bandwidth is required for TV signal transmission. When signals are transmitted in analog form, the carrier should have double the upper bandwidth. The normal TV communications has a bandwidth of 250 MHz and therefore it can simultaneously transmit 20 TV programs. However, instead of microwaves, if the light waves are used as a carrier wave, the bandwidth will be about 10 to the power 8 MHz and can therefore transmit about 10 to the power 6 TV program at a time. Thus, the use of the light waves expands our communication capacities tremendously. Next, sensor. Optical fiber used as a sensor. The variation of refractive index of the optical fiber under the influence of external forces is utilized in fabrication of optical fiber sensors. If the optical fiber is subjected to heating, the temperature causes a change in the refractive index of optical fiber. As temperature increases, the difference between the refractive indices of the core and cladding materials reduces and light tends to leak away from the cladding. A simple thermometer can be built using LEDs as a light source, a coil of the optical fiber as heat sensing element, and a photo detector to measure the intensity of light. Temperatures in the range from 80 degree to 700 degree are measured using this technique. A smoke and pollution detector can be built using optical fibers. A beam of light radiating from one end of the fiber can be collected by the another optical fiber. If foreign particles are present in the region between the two fibers, they scatter light. The variation in intensity of light collected by the second optical fiber reveals the presence of foreign particles. A loop of optical fiber can be used to determine the level of the liquid in a container. A part of the cladding is scrapped and the fiber loop is suspended above the liquid level. Light is directed to pass through one end of the fiber and its intensity is measured at the other end. A bar core loses more light when it is immersed in liquid than when it is in air. Therefore, a sudden change of outgoing light intensity indicates the liquid level. And LEDs, MMF, and a photo detector are used in fabricating such a liquid level sensor. Such sensors are used to monitor and filling our petroleum tanks. Double refraction induced in the optical fiber when external forces are applied. If the property of induced double refraction is exploited in the fabrication of some other sensors. The important role optical fiber communication play the important role in the field of the medicine. The optical fiber endoscope is used to inspect internal organ for diagnostic purposes. In ophthalmology, a laser beam guided by optical fiber is used to detach the retina and to correct defective vision. In cardiology, optical energy transmitted through a optical fiber is used to evaporate build up plaque and is blocking an artery. In the treatment of cancer also, the optical fiber technology is used. The process involved injection of special chemicals that penetrate only the cancerous cells. Infrared energy is transmitted via the fiber eliminate the affected area and is absorbed by the special chemical in the cancerous cells. The heat generated destroy the cancerous cell. In a military, we also use the optical fiber, and it plays the important role in the military area. An aircraft, a ship, or a tank need ton of copper wire for wiring of the communication equipment, control mechanism, instrument panel, illumination, etc. Use of the optical fiber in place of the copper reduced weight and further maintains true communication. Silence to the enemy. For example, a shipboard radar system require about 250 meter of coaxial cable, while a weight of 7 tons and a diameter of 45 centimeter. Remember it. These cables can be replaced by the optical fiber weighing 20 kg only and measuring 2.5 centimeter in diameter. Fiber guided missiles are used in recent wars. Sensors mounted on the missile transmit video information through the optical fiber to a ground control van and receive commands from the van again. The control van continuously monitors the course of the missile and if necessary corrects its course to ensure that the missile precisely hits the target. Optical fiber communication system can be broadly classified into two groups: local and intermediate range system, where the distances involved are small, and long haul system, where the cables span large distances. Let me discuss local area network. The local area network, short name LAN, is a computer oriented communication system. LAN operates over short distances of about 1 to 2 km. It is multi-user oriented system. In LAN, a number of computer terminals are interconnected over a common channel, allowing each computer to use data and program from any other. An optical data bus offers a great reduction in cost and increases enormously the information handling capacity. Next one is the Longhorn Communication. One of the most important applications of optical fiber network. Longhorn communication system are used for long distances, say 10 km or more than 10 km. Telephone cable connecting various countries come under this category. A rather sophisticated long haul network is a NSF net, which links 6 supercomputer centers throughout USA. Well, it is the backbone of the internet. Optical fiber, network is the backbone of the internet nowadays. The optical fiber cables lie in the seabeds and transmit the signal all over the world. So, this is the main applications. These are the main applications of the optical fiber systems. These are the references. If you want more query about the optical fiber system and research papers, you can go through these references. At last, thank you all participants.